This is my Lab 2 presentation for Physics 1. This lab involved collecting data on real-world projectile motion using Tracker, and then coding the predicted motion of the object twice with GlowScript, once with and once without drag force. So the parts of this lab were to first record a two-dimensional projectile motion, upload that video into Tracker, and then extract the positions and average velocities in both the x and y plane, or directions. Then I used the initial position and the initial average velocities to create computational models in GlowScript that would predict the trajectory or the positions of the projectile. One model was created using just gravity, and the other model used both gravity and drag force, and then I compared the expected and predicted positions in the end. The fundamental principles used in this lab are Newton's second law and projectile motion. Newton's second law is what we derive velocity and position update formulas from, so specifically in this case, which are the ones that are specific to constant acceleration or constant net force, which Newton's second law also allows us to predict certain things about the motion if the net force is constant, which it is in the case of projectile motion, which we learned about in class, and we learned about the components involved in it. The net force is usually just made up with gravity on Earth and air resistance or drag force, which have the formulas given here. The projectile motion in this case was me throwing a paper ball or a wad of paper into the air. The system was the paper ball. The surroundings were everything else, like the table, air, etc. The initial force was the throw, and notable other forces during the motion were gravity and air resistance, or drag. And here you can see the extracted positions and average velocities calculated using Tracker. So in GlowScript, first I predicted the motion without drag. I did this by just using force of gravity as my net force and plugging that into the velocity and position update formulas, making sure to use average velocity in the position update formula. And here you can see the predicted trajectories calculated by this model. In my second model, I included drag as well, so force net was calculated by adding force of gravity and force of drag, which was calculated using the formula provided. And the proportionality constant that goes into that formula, or B, was found by me, or set by me, using a lot of trial and error and just finding a proportionality constant that would make the model more accurate than the one only using gravity versus less accurate, and I settled on 0.002, which is very small, but it's because, as I saw while I was throwing the ball, because like the mass was so light and because of the material, it did not experience that much drag, or air did not slow it down that much. Here is the calculated trajectories found using this model. And now here you can see all three, so the one with Tracker and the two GlowScript models compared together. On the left is the predicted versus actual x positions. They're all very similar but slightly off. As you can see though, the yellow line, or the GlowScript model with drag, is slightly closer to the blue line, or the Tracker position, than the red line, which is GlowScript no drag. On the other hand, on the right, the Y positions, the Tracker one is slightly off from the two GlowScript ones, but again, if you can see, the yellow line, or the GlowScript with drag, is slightly closer to the actual, or the Tracker position, than the GlowScript no drag. So this is probably because of some errors. First, the drag constant was found by me in a very trial error guessing sort of way, not very technical. Also, the 2D video, the video was meant to be 2D and only operate in the X and Y dimensions, but it wasn't shot completely steady and at a perfect angle, so it might have unintentionally introduced some three-dimensionality, or Z components, into the positions, which would have messed some of the calculations up. And then the mass of the ball was just Googled by me, but wasn't actually measured at the moment. I just Googled the mass of a piece of paper. But overall, the model with drag is slightly closer to the actual motion versus the model without drag. There is some margin of error though, especially in the Y position, but it does show how projectile motion is very predictable. In terms of terminal velocity, the velocity versus time graphs in glow script curves slightly, which means the speed differs slightly. It isn't fully constant. That probably means that it's affected by some other forces that weren't fully calculated. But again, if I did this experiment again, reducing my errors and maybe making it even more like foolproof, like gravity and air resistance are the only two forces, we could probably get terminal velocity. And if we threw the ball up, the velocity would stay the same, but it would just reach the ground faster because there would be no x displacement.